Welcome to Chapter 9, you guys. This is our last chapter of the semester due to all the things that have happened so far. I hope to get you guys far enough into this chapter to fully appreciate what's going on. So the story in this particular chapter is all about exponential and logarithmic functions. So exponential functions, they are highly useful in scientific and engineering applications, and they're good to know no matter what career one chooses. Essentially, they end up being like y is equal to 2 to the x, g of x is equal to, 1/3 to the x power, etc. And what it really means is that you're looking at functions whose variables are actually the exponents in the expression. They are able to predict for us population growth, radioactive decay, all kinds of things in engineering, like I said before. So I'm going to break this chapter up into 3 pieces. The middle piece is going to be kind of short, but the first piece is going to be this particular video. We're going to talk about function compositions. When we're done with that, we will take a brief look at one-to-one functions, and then finally, what are inverses and how do we find them? Okay, so that might be the longest one of them all, but in order to get to exponential and logarithmic functions, okay, we need to go through this section and know the nuts and bolts of this particular topic. Okay, so let's get going. A composition of a function. Okay, you compose functions by inputting one function into another, and I give you an example. So, for example, let f of x equal to the square root of x function, and let g of x be the function 2 times x minus 5, okay? So the notation is funky, but it is also helpful maybe to see a picture. So what I've got is a function that says, hey man, I am f of x, and f of x, what it does, you give it a number, it gives you the square root. So there's an input and an output kind of thing going on. Okay, so for example, if you were to take the number 9, plug in here, you would get 3, because what it does is it square roots 9. Okay, so in the work inside here, the inner work is this. Okay, now if I compose another function with that, that is to say, if we're in step 1 here, or comment 1, inputting g of x into f of x looks like this. It's got some crazy notation. Okay, so what it's doing is you're just going to take 2x minus 5 up here and plug it into f, as you can see here, and I'll explain the notation in a second. But talking about functions in line with each other, it's really it helped me to look at it this way: 2x minus 5. And so you got these input places and whatever. And so what happens is you get rid of, just one function, and you're going to be inputting into two one at a time, like a daisy chain. So, for example, thinking of something, you can go, well, let's see if I can come up with a clever one. Let's see, that would be, oh, golly gee, Hossafat, that would be 21. Okay, 10.5. All right, let's do 10.5. So 10.5 is going to be plugged into here, and the computation would be 2 times 10.5 minus 5 is equal to 21 minus 5 is 16. So out pops 16. Now I chose that number so that I got, a nice perfect square, right? But the composition's not done, because what happens next is you take this number and plug it into the next function, which is the square root function, and you get the square root of 16, and out pops 4. Okay, so we start with 10.5, we plug it into g, we get 16, we plug that into f, we get 4. And now the whole thing can be done this way. We would say f of g of x, okay, that's how you write it, is f of what? 2x minus 5, which is the square root of 2x minus 5. And now I draw a straight line there just to show you something. You ready? So when we decide to plug in, say, x is equal to 10.5, well, the whole thing is done. What happens is the square root waits until you figure the thing out on the inside, right? And we already did the math. You get square root of 16, and it ends up being 4. So putting functions together, we see these all the time. We've seen this a lot. We've just never called it a composition of functions. So, for example, if we were talking about a parabola, like, oh, y is equal to not x squared, but how about x minus 2 quantity squared? That shifts it which way? Right 2 units, remember? But it's a composition of functions. It's a composition of one function, call it f of x, is x squared, and then g of x is x minus 2. Now, no one ever called it that until now. Here we are, we're talking about it. Okay, so up here are some notes for you guys to take a peek at. On number 1, I said there's this funky notation that we have to get used to. I started here, and I just said, oh, f of 2x minus 5 is just plug 2x minus 5 into the square root function, because we have these guys defined up there. So when they say f of g of x, you take g, you plug it into f. If they say g of f of x, you take f and plug it into g, okay? And then it gets weird. I have some more examples here, and I have another page where we can talk about it as well. So there is f of f, there's g of g, that kind of stuff. Let me get to a new page and kind of clear up the notation, okay? So in the notes, when I give them to you, you can pause it, you can look at this and see if it makes sense to you, some strange stuff. But we're going to do the same thing on the next page, okay? Some good notes for you to see. I'm giving you examples of f of g, g of f of f, and g of g. Strange, right? Well, it's stuff we've done a lot. We do a lot in mathematics. Okay, the notation. So if it says this, okay, you read that as f of g of x. Okay, so in other words, it's going to be equal to the same thing as f of, and now you plug in whatever you want. Remember, f is a function. You know, if f of x, for example, let me grab this guy right here. Let's say that f of x is x squared minus 5, okay? Then we know if we wanted, f of 2 is 2 squared minus 5, turns out to be negative 1, okay? We can plug in anything we want. We can plug in 5 in there, is 5 squared minus 5 is 20. But you can do other things too. So the notation expands to say, plugging in, oh, I don't know, f of the square root of 2x plus 5. That would be the square root of 2x plus 5 squared minus 5. You see what I'm saying? So every time you plug in, you're plugging in for x, 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 even this for x, okay? And then you can clean it up. I look at this as that little O is like Irish, F-O-G, you know, you speak it with an Irish accent. So it just means f of g of x. I don't like this notation. You don't see it anywhere else except in an algebra book. But what it means when you're doing your homework, you could tell yourself it's f of g of x and then go forward. So here come some examples. You ready? Okay. So the functions we're playing with, you want to stay focused on them. There's this one and this one, okay. And they're going to ask us to do a few, I'm going to ask you to do a few compositions, okay. So the first one is, let's read it together, f of g of x. We rewrite it as f of, you can skip this step, but I'm not going to do it. I'm not going to skip it. And then I go f of, okay, what is g of x? Do you see the definition right there? F of 4 over x, okay. And so what does f do to it? F takes anything, look what this function does. We were playing with them over here, right? F takes whatever you give to it, 4 over x in this case, squares it and subtracts 5. It's just a machine. Bum, 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 bum. Here's a 5, here's a 2, here's a negative 1. Here's the square root of 2x plus 5. Here's a 4 over x. It just squares it and subtracts 5 and spits it out. So what we do with that is we go, you know what, I got an answer of 16 over x squared minus 5. Pretty happy with that. Okay. Now I'm going to go down on the left column, and then I'm going to jump back to the right. Okay. Let's not lose our mojo, as it were. Now let's do g of f of x. Well, g of f of x is really plugging in. Basically, in the first one, we plugged g into f. Did you notice? Let's do that. Okay. In this one here, f of g of x, we took g and it goes into f where x is. This time we're going to take f and plug it into g where x is. So it's going to be, well, g does this. It goes 4 divided by whatever you give it. okay? And what are we giving it? We're giving it f of x. And you know what? It's good sometimes for me to do some color coding on this too. So let me get this going on. We plugged in 4 over x, and it looks like this when you plug it into the f function. Now we're going to take the f function, which is, oh yeah, let me do one more step. That's the same as g. Well, what does g do? G does 4, no, don't do that yet. G of, okay, what are we plugging in? What is f? It's x squared minus 5. I'm reading it up top there, okay? Getting kind of busy. Let me erase those guys, if I can. Okay. And now, what does g do? G takes something and goes 4 over whatever you give it. What did we give it? We gave it x squared minus 5. Do we do anything more with this? No. Let me rewrite it. It's 4 over x squared minus 5. So instead of 4 over something, it's 4 over, you tell it what? In this case, x squared minus 5, which is f of x. So one function going into another. You can get weird. You can go like, what's f of x? Well, what you do there is I've got f of itself. And what is itself? Remember what f is? It's f of, and as I recall, it is x squared minus 5. What does f do? It takes something, squares it, subtracts 5. Here's what it looks like when it does it to its own self. Weird, right? And I don't need to multiply that out. If you want to, you can, but I'll just write this as what I have is x squared minus 5 squared minus 5. It seems unnatural. It's okay to do. Here's one more. G of x. Oh my goodness. That's g of itself. Okay. So it's g of what is itself? 4 over x. As I recall, it's 4 over x. And what does g do to things? It takes things and puts it under 4. What are we taking under 4? 4 over x. I might want to clean that up a little. Maybe I write it as 4 over 1 times x over 4. Look what we're getting, just x. All right, interesting. Okay, that's called composition of functions. Now I'm going to go back up to the right column and see all the work we did. And remember we did f of g of x. Now this is asking for f of g of 4. Before you think I've got to do it all over again, guess what? You don't. Because if you have a formula for f of g of x, which we do, then if we wanted f of g of 4, all I'd have to do is take this function, which is 16 over whatever squared minus 5. I'm using this function, and I'm plugging in the number 4. Okay? So I don't have to reinvent the wheel. The wheel has been invented, f of g of x. So all I have to do for f of g of 4 is plug in 4. Isn't that cool? So what you have is 16 over 16 minus 5. Oh, cool. We get 1 minus 5. Guess what? Negative 4. I can imagine where sometimes you might get undefined, you know what I mean? Or something, or I mean, even an imaginary number, perhaps. Okay, let's do this next one. Well, this one's asking for g of f of 4. Okay. But we have a formula for g of f of x, and it is 4 over whatever squared minus 5. And I have us plugging in 4 all the way down the line, so let's see what we got. We got 4 over 4 squared is 16 minus 5. Guess what? Looking like 4 over 11. What do you think? It is what it is, okay? And this thing, it just gets you used to plugging one function into another. The reason we're doing this, you'll find out in just a second. Let's finish all these guys. So f of 4 is f of, f of 4. Some people will do it this way. They'll go, well, what's f of 4? And they'll compute it. Then they'll come back and plug that into f again. You don't have to. It's all done right here. You just simply go, it's equal to the square of whatever squared minus 5 squared, okay, minus 5. And the whatever we're plugging in is 4 again. That's what I chose as my guinea pig number. And we're getting, it looks like we've got 16 minus 5 squared minus 5 is 11 squared minus 5 is 121. Oh, this one's a tough one. Is 116. All right. This one's the toughest one of all. Not. This says, what's g of 4? Well, look at this guy says. It's equal to whatever. And the whatever we're plugging in is 4. This one is simply 4. Okay? Yeah, there's a reason. There's a method to our madness. What it is basically when we take functions like that are inverses of each other, what we're going to study are the functions y is equal to 2 to the x and y is equal to log base 2 of x. These guys are going to be found to be inverses, but when you take inverses, like for example, the cube root of x cubed, you get x. If I take the cube root of x and then I cube that, I get x. These guys are inverses, and that happens with inverses. So knowing how to take compositions of inverse functions of any function whatsoever is important to us. And it depends. If you go farther in math, then it becomes even more important when we get into calculus and stuff, just to be able to see compositions of functions. Okay, I think that's it for this particular section. Yep, the next stop, 1-to-1.